Hello everybody. Today is our first session of class 11 physics, and in this session today we will deal with the two important topics in the second chapter of your textbook, that is units and measurements. In this chapter we actually deal with the measurements of physical quantities. So let us start with the physical quantities. You know there are base fundamental physical quantities and also derived physical quantities. There are 7 base or fundamental physical quantities, which are base quantities, as you know, are first we have mass, which is having an SI unit of kilogram. Then we have the base quantity length, whose SI unit is in meters. Then we also have time, whose SI unit is in seconds. Then we have temperature. SI unit is in Kelvin. Then the fifth one we have is the amount of substance, which you must have come across in chemistry. Amount of substance. SI unit is the mole, MOL. If you haven't come across this yet, you will be doing this in chemistry this year. Then we have electric current, which you have done in 10th standard. Electric current is also a base quantity, whose SI unit, as you already know, is in amperes. And luminous intensity, you must have come across intensity in the chapter on light in 10th standard. If not, you will be learning this in 12th standard. Luminous intensity, to do with the intensity of electromagnetic radiation, whose SI unit is candela. Along with these 7 base units, 1, 2, 3, 4, 5, 6 and 7 base units, we have 2 more base units. One is the plane angle, which you are familiar with, whose SI unit is in radians. You measure plane angles in radians. That means if you have something like this, this angle here is 90 degree. So any angle here, this is a 90-degree angle, and you know that these angles are normally represented as 90 degree or its SI unit is in radian. So angle which appears on a plane, that is what we have as a plane angle, represented as radians. We also have solid angles. Solid angle is actually a 3-dimensional angle. SI unit is T radian. SI unit is T radian. T radian, which is actually, see, suppose you have a cone like this. You will see that inside the cone, what you have is a solid angle. So you will see that there is a solid angle inside the cone, and that solid angle is what you call as, its SI unit is what you have as T radian. So plane angle is always an angle that appears on a plane. A solid angle is a 3-dimensional angle. So this is what you call as a solid angle, whose SI unit is in T radian. So we need to have these base quantities if in case you want, in order to get these derived quantities. So we have 7 base quantities plus plane angle and also solid angle coming under the base quantities. Let us look at what are the derived quantities. Some of the derived quantities that you already know. We'll start with that. So you'll be familiar with what you mean by derived quantities. Let's look at area. Now, area of a rectangle, as you know. So we are now going to discuss derived physical quantities. Okay? Derived physical quantities. Let us look at the area of a rectangle. So area, we know, is for a rectangle length into breadth. Both length and breadth come under the base quantity length. So because you're multiplying the two, you have its SI unit as meter into meter, which will be meter square. Similarly, suppose you are going to take the volume of a cuboid. Volume of a cuboid would be length into breadth into height. length, breadth and height of that cuboid are measured in base quantity length. So we have the SI unit as meter into meter into meter. We have this as meter cube. Let us look at something else like velocity. Velocity in 9th standard you have learned as displacement by time. Displacement is the base quantity length. Time is also a base quantity. So by dividing these two base quantities, you get what we have as velocity, which is a derived quantity. So this will be displacement in meters divided by time. So its SI unit will be meter per second. If you have, let's say, acceleration. Acceleration you've already learned in 9th standard as velocity by time. This velocity is displacement by time. So you have displacement by time into one more time here. So this displacement is a base quantity. Time is another base quantity. So from base quantities you get your derived quantity, that is acceleration. So its SI unit will be meter per second square. So I hope you have now understood that from the 7 plus 2 base quantities, you can get any number of derived quantities. So these are the physical quantities that we will be dealing with in this chapter and in the chapters to come. Either they are base quantities or they will be derived quantities. Now, since we are starting this chapter with measurement, we will first discuss a method to measure large distances. For example, suppose you were to measure the distance of a star from the Earth. Then you can use this method, which we call as the parallax method. So this parallax method is used to measure large distances. Here, let us imagine this is the Earth. This is the Earth, representing the Earth. And from the Earth, you are expected to find the distance of a distant star. Okay. Now here, I am going to take two diametrically opposite points. I have point A and point B. So from two diametrically opposite points, let's say this distance between the 2 points here on the Earth is B. From here, there is an observatory. From this observatory, I am going to view the star. I am going to view the same star from another observatory at B at the same time. So this star is being viewed from two different observatories, and these dotted lines represent the direction of viewing the star from the two observatories at points A and B. This angle is what you call as theta, that is the parallax angle. So by parallax angle, we mean the angle between the two directions of viewing the star from two different points on the Earth. Now, to measure, so what we need to measure here is this distance capital D of the star from the Earth. Now, in order to show you how to measure this distance D, let me consider the star as the center of a large circle, and the radius of the circle is going to be this capital D, so that this distance B is a distance between 2 points A and B, like this. Okay, so we have the distance star as the center of a huge circle whose radius is D, and this 2 points I've taken as the chord of that circle. Now, because this small b is much lesser than this distance. This distance D is supposed to be very large. So B being much lesser than D, you may approximately take this as the arc length. And I'm sure in some smaller class in geometry, you have learned that the arc length of any circle is equal to its radius into angle theta subtended at the center here. So I hope you know this formula already from geometry in some smaller class. Arc length of any circle equal to radius of that circle multiplied by the angle theta that this arc subtends at the center. So from here, I may write that arc length is what we have approximately taken to be B. So we may write B is equal to, radius of that circle is this capital D multiplied by theta, or this B is a distance between the two diametrically opposite points that we have taken on the earth. Capital D is the distance D that you've been asked to measure, that is the distance of the star from the earth, and theta is what you call as the parallax angle. So you may find out D using the formula B by theta. So this method is used to measure large distances, and this method is what you call as the parallax method. Okay. Now we go into the next topic that I said we will discuss today, which is called dimensions and dimensional analysis. Dimensions and dimensional analysis may be a new topic to you. I don't think you have come across dimensions in any of the smaller classes, but it is an important topic in class 11. Now let us consider the base quantities, mass, length and time. Suppose I am going to represent mass with a capital M, length with a capital L, and time with a capital T. Okay. Now suppose we want to represent the derived physical quantity velocity. So we know velocity is equal to displacement by time. And displacement, the base quantity is length, because displacement is measured in terms of length, divided by T, time. Now I may represent this as L T raised to minus 1, because when I bring this T to the numerator, power is minus 1. Length is already in the numerator, so 1. But mass does not appear in the formula for velocity. So I may write mass raised to 0, m raised to 0, because anything raised to 0, I hope you know, is 1. So I may write m raised to 0, because this will anyway be 1. Then I have L raised to 1, which is represents displacement in the numerator. T raised to minus 1 represents time in the denominator. So now when you look at this, these powers 0, 1 and minus 1 are the powers to which the base quantities, mass, length and time, have been raised in order to represent this physical quantity velocity. These powers are what you call as dimensions of velocity. Dimensions of velocity. Let me give you one more example. Let us take acceleration. Now acceleration, as you know, is what? Velocity by time. Velocity by time. The dimensions of velocity we know is power is m0, L1, t raised to minus 1 for velocity, divided by t. If I bring this t on top, there is one more minus 1. So this will now be raised to minus 2, because I brought this t on top. So the powers 0, 1 and minus 2 represents the dimensions of the physical quantity acceleration. So basically, I hope you understood that dimensions means the powers to which the base quantities mass, length and time must be raised in order to express or represent a physical quantity. This is what you call as the dimensions of a physical quantity. Now suppose you were to represent this in square brackets like this. Suppose I am going to put a square bracket with the base quantities raised to their dimensions. Then this is what you call as the dimensional formula of acceleration. Similarly here, you have the dimensions of m as 0, 1 and minus 1 for velocity. If you represent it in square brackets, that is, in square brackets you represent the base quantities raised to their dimensions, then that is what you call as the dimensional formula of velocity. So dimensions simply mean the powers to which the base quantities have been raised. Dimensional formula means you express the base quantities in terms of their dimensions in square brackets, and that is what you call as the dimensional formula of that physical quantity. Again, if I now write an equation where I am equating the physical quantity, let's say this is acceleration, to its dimensional formula, then this is what you call as a dimensional equation. Let me give you the example, another example. Let's say I'm going to represent volume, okay? So volume, I represent the physical quantity as volume V equal to, volume we said is what? Length into breadth into height, which is, all of them are in terms of length. So it will be simply L cube. Mass does not appear in the formula. T does not appear in the formula. So the dimensions of volume are 0, 3 and 0. So if I am now going to equate the physical quantity to the dimensional formula m0 L cubed and T raised to 0, then this is what you call as the dimensional equation of volume. Here we have velocity with a small v. Here I've used a capital V, and so this is also a dimensional equation now because I've equated the physical quantity to the dimensional formula of velocity. This is what you call as dimensional equation. So you must know what you mean by dimensions. They are simply the powers to which the base quantities have been raised in order to express a physical quantity. Dimensional formula would be to represent the base quantities with their dimensions in square brackets, and when you equate that dimensional formula to the physical quantity, you call that as a physical dimensional equation. Okay. Now in your textbook we have 3 applications of this dimensional analysis. The first application is you can check whether a given equation is correct or not by using dimensional analysis. And for this we use what we call as the principle of homogeneity. Principle of homogeneity simply means it says that your equation is correct only if all the terms in that equations have the same dimensions. If they don't have the same dimensions, if all the terms do not have the same dimensions, then that equation is incorrect. Or in other words, you can add or subtract physical quantities only if they have the same dimensions. You may multiply, but you cannot add or subtract physical quantities unless and until they have the same dimensions. Okay, I will explain this further using an example. You must have learned the 3 equations of motion in 11th standard. The first equation of motion, you must have learned this equation in 9th standard. The 3 equations of motion. One is V equal to U plus AT. Then the second equation you must have learned is S is equal to UT plus half AT square. Then V square minus U square equal to 2AS. Let us check the second equation whether it is correct or not. Okay. So we have this equation, S is equal to UT plus half AT square. Now the principle of homogeneity says this equation is correct only if all the terms have the same dimensions. Let's see which are the terms. Displacement is one term, U into T is the second term, then separated by a plus or a minus sign. You're adding or subtracting terms. So this becomes the third term. So if S, the product of UT and half AT square, all these 3 terms have the same dimension, then you may say that this equation is correct. So let us check. The first term is displacement S. Okay. Displacement, as you know, is measured in the base quantity length only. For displacement, your dimensional formula will therefore be mass raised to 0, L raised to 1, T raised to 0, because displacement is simply base quantity length. Mass and time do not have any dimensions there, 0. Next we are going to take the term U into T. U is the initial velocity. You know that in this equation, U stands for, what is S? S is the displacement of the particle in time t. U is the initial velocity of the particle. A is the acceleration of the particle. Velocity, whether it is initial or final, velocity will always have the same dimension. And I hope you remember the dimensions for velocity. Velocity is displacement by time, and therefore displacement in terms of length divided by time, and therefore we have m does not appear in the formula for velocity, So raised to 0, L is in the numerator, raised to 1, T in the denominator, raised to minus 1. So this is your dimensional formula for velocity. Multiplied by dimensional formula for time. Dimensional formula for time, the only base quantity that appears in time is time. So we have m raised to 0, L raised to 0, T raised to 1. Now when you multiply them, the powers will get added up. So if you multiply these two, you have m raised to 0 plus 0 is 0, L raised to 1 plus 0 is 1, and T raised to minus 1 plus 1 is 0. So that is a dimensional formula for the second term. Look at the third term is half AT square. Now half is just a number. So numbers do not have any dimensions. So you may ignore that half. So this is equal to acceleration into time square. Acceleration, I hope you remember, is velocity by time. So velocity has the dimensional formula as m0 L raised to 1 T raised to minus 1 divided by time. If I bring this on top, there is one more minus 1. So we have m raised to 0, L raised to 1 and T raised to minus 2. So this is the dimensional formula for acceleration. So I'm going to use that here for our half AT square. So we have the third term as half AT square. So this is half, you ignore because it does not have dimensions. Acceleration is, we just found out, is m raised to 0, L raised to 1 and T raised to minus 2 multiplied by time square. Time square, base quantity is only time. So m0, L0 but time square. Now we're going to multiply this, which means the powers will get added up. So we have here m raised to 0 plus 0 is 0, L raised to 1 plus 0 is 1, T raised to minus 2 plus 2 is again 0. So now you will see all the three terms. S has this as a dimensional formula, m0 L1 T raised to 0. Ut, the second term, also has the same dimension, m0 L raised to 1 T raised to 0. The third term also has the same dimension, m0 L raised to 1 and T raised to 0, which means your equation is dimensionally correct. Okay, I will show you one more example, a simple one. The third equation of motion. The third equation of motion is v square minus u square equal to 2as. Okay, that's the third equation that we have, equations of motion. That is, third equation of motion is v square minus u square equal to 2as, which I hope you know. V is the final velocity of the particle, u is the initial velocity of the particle, a is the acceleration of the particle, and s is the displacement of the particle. Now how many terms do we have here? This is one term separated by a subtraction sign. So this is a second term and this is the third term. So we have three terms. And this equation is correct only if all the three terms have the same dimension. We already know this equation is correct. I'm just teaching you with a simple example so that you will know how to check, given a complicated equation, how do you check whether that equation is correct or not. This we already know is correct. So let's check. V square. Dimensions of V square is, dimension of velocity I just showed you is m raised to 0, L raised to 1, T raised to minus 1. This was the dimension of velocity. Whether it is final or initial, it's the same. So this raised to 2 because it's squared. Now when powers are raised to another power, you multiply. So this is equal to m raised to 0 into 2 is 0, L raised to 1 into 2 is 2, and T raised to minus 1 into 2 is minus 2. Okay, because we are multiplying because this is raised to another power 2. Then we take the next term, that is u square. Dimensions of initial velocity will be the same as final velocity because both are coming under the same derived physical quantity, velocity. So this will be m0 L raised to 1 T raised to minus 1 again raised to the power 2 because this is also square. So we have m0 L square t raised to minus 2. So now we see that the first term and the second term have the same dimension. Let's check this last one. Third term, 2as. 2 I told you is a number without a dimension. Acceleration in the previous equation, we derived it as m0 L raised to 1 t raised to minus 2 multiplied by displacement. What is S? S is the displacement of the particle which comes under length. Base quantity is only length. So we have m raised to 0, L raised to 1, t raised to 0 because displacement is just base quantity length. Now if you multiply, m raised to 0 plus 0 is 0. Length L raised to 1 plus 1 is 2. And t raised to minus 2 plus 0 is minus 2. So let us check. The first term has m0 L square t raised to minus 2. Second term has the dimensions m0 L square t raised to minus 2. And the third term also has the same dimensions m0 L square t raised to minus 2. And because all the three terms have the same dimensions, we know that equation is dimensionally correct. Okay, so we've just done two simple examples. We will continue in the next session with other examples of the same application, and also we have two more applications of dimensional analysis. In your textbook, first textbook, on page 214 and 215, you will see they have printed out the dimensional formula for many physical quantities. So I will send you a list of the physical quantities whose dimensional formula you must by heart, because for doing these problems, you need to know the dimensional formula by heart. So I will send you the list. You please learn all the dimensional formula for those physical quantities by heart. Okay. Thank you.